And thanks everybody. Today's talk is kind of twofold. The main goals are going to be to hopefully have you all walk away and understand a little bit more about mechanisms of injury in a pitcher. But then also I want to spend some time touching on deriving some machine learning models, because I think in this day and age, that term is tossed around so much. And I struggled with this for a long time, understanding what the heck is machine learning. So I think it's important to try to go through some of the derivations on it. And then just for our future's sake, I think it really is real and impactful. And I reflect on this a lot. What's my future going to be like in a career or even in sports in general with machine learning here? And so we'll give you some examples on how powerful it can be. And yeah, that's kind of the scope for today. As you mentioned, I'm from Wisconsin, so it's a really big treat to come back and present. I grew up in Beloit and did my undergrad at MSOE and got to play some baseball. So that's where a lot of this exposure to biomechanics and my own injuries came to first fruition. And then, yeah, in 2012, we started Motus Global. And our goal at the beginning was to take what we do in a clinical lab, which is motion capture, and eventually bring it to the mass market. So at the time, we operated a 3D lab where we would test athletes, a variety of athletes in all kinds of sports. Pitchers were the primary population. And then we'd work with strength conditioning, physical therapists, performance staff members to individualize training plans. So that was like our first step into the space. But then as wearables began to reach a hype in like 2013, we started developing wearable technologies that allow us to do some of what we do in our lab, but now out in the field. So in 2014, we made our first launch. It was a smart compression sleeve with a sensor embedded right below the UCL and the elbow. And it was fortunately approved by MLB. It was the first wearable allowed for in-game use, and that was in the 2015 championship season. And since then, we've aggregated millions of throws, and that not just at the MLB level, but at the college, high school, and youth level, and are starting to get some good insights into what predicts injury and have some tools to help prevent it. So the sensor itself, it's a 6-axis inertial sensor. It's got a really high-end gyroscope and accelerometer to tolerate the forces of a pitch. We sample at 1,000 hertz, and essentially it works like a Fitbit, but on your elbow. So you go out, you throw all day, it stores all of the throws, and then we download at the end of the day and calculate all the physics on each throw you make. The app itself, on the advanced side, we can give some raw metrics with every pitch. There is something called max shoulder rotation, so during the pitch we can measure how far back you rotate. We can pick out the arm slot at ball release, so this would be at 0, 45, 90-degree arm slot. We can get rotational velocities, but most meaningful is the peak stress on the elbow. So we can do some inverse dynamics to calculate valgus torque. And that's what feeds into all of our workload algorithms. I show Motus Cricket. So we actually use this for a variety of overhand sports too. We do quarterback passing, we do cricket analysis, we do volleyball analysis as well. But yeah, so before we get into some data examples, I have to make some definitions. So we did pioneer these concepts of acute and chronic workloads. Dr. Tim Gavitt did with GPS data. What we have found is when we apply it to the joint, it's much more powerful, and it tells a good story conventionally. But so first off, we'll take daily workload. We calculate that by adding up all of those stress levels for every pitch you make in a day. So there's different effort levels. Not every pitch is created equal. So we add that up, and that's daily load. And then we can measure a rolling 7-day average, and then we call that acute workload. So that's your short-term fatigue. And then we also measure a rolling 28-day average, and that's called your chronic load, a longer-term average. And the concept is a pitcher builds up fitness or chronic workload, and then they can sustain acute pushes a little bit further. And we quantify that with one number called the acute to chronic ratio, an AC ratio. Simply, it's just your weekly load divided by your average monthly load. And it serves as a really nice number to gauge. So backing up to chronic workload, typically there's this progression in a pitcher's season. Early on in spring training, they build up a chronic load slowly. You maintain it in season, and then there's an offloading as you take rest. If you look at a lot of the injury reports, you'll see a lot of the injuries occur pre-season when you're building up workload, and it makes sense. We have a throwing program for a reason. We slowly introduce workload because we know our arms need to build up fitness. The problem we run into is not everyone is doing the same effort with every pitch, so oftentimes we see a really big acute spikes. And here's kind of a quick at-a-glance view of what that AC ratio is correlated to. So Starting with just the number alone, if it's at a 1, that means your weekly workloads are about the same as your monthly workloads. When we see a 1.3, that's a 30% spike in your acute load. And our research has found that's about 1 standard deviation from a normal season. And so when we look at injury risk about this side of a 1.3, we see the injury risk above a 1.3 is much higher. So Dr. Samir Mehta did a really good research study with about 200,000 throws, and they found that an AC ratio above a 1.3 led to an injury risk factor of 2.2% on that given day. And then below was a 0.08%. It's about a 25-time increase in injury likelihood just from that measurement alone. Second feature of this kind of data is that a high chronic load can be protective of injuries. So this is a heat map of injuries from Dr. Tim Gabbett with GPS data. But looking at a chronic load of 100, no matter what these athletes did the following week, the risk of injury remained the same, about 3.5% to 4%. But then when the chronic load dropped, and then they had a subsequent acute spike, so 60 with a 90 acute, the risk of injury doubled. And that trend continues to follow. So the lower the chronic load, the higher the spike, the higher the risk of injury. So what we're saying is a high chronic load can be protective of injuries in pitchers as well. So let's look at some real data though. So this was grade 2 UCL sprain from an MLB pitcher. This was one of our first data sets early on that showed this trend. What we have is acute workload, this chronic load, and that AC ratio we talked about. So if you look at these acute spikes, I mean, they're natural, nothing too high, but there's cyclical patterns in a pitcher's regimen. They sometimes pitch deep into games, or if they're relievers, they pitch back-to-back days. Maybe they had too much of a bullpen one day. But coupled with a high chronic load, we had no problems. It was about a 1-2, a 1-3 ratio. Around the All-Star break, the pitcher took some time off, and we saw a really big dip in that chronic workload. And unwittingly, he came back with the same effort. He had an acute workload that day after the All-Star break, and because he had such a low chronic load, the AC ratio was at 2.1 on the day of the injury. So again, time and time again, not only just internally in our own data sets, but from third-party researchers, we have people seeing that this AC ratio, when it spikes, is a major risk factor for injury. This was some fun stuff we just pulled out. So we wanted to look at Nolan Ryan. Now we don't have motusTHROWs on him, but if we look at just his pitch counts, you can calculate a chronic load and an AC ratio. So 1974, picked this year for a reason, because one of his games, he threw 235 pitches in one of the games, but this is his chronic workload. You can see early on there's an increase, there's a maintenance period, and then he had this period where he kind of fell off a little bit because of the All-Star game, and that was on July 20th, a little later back then. And then he came back right up. But if you look at the AC ratios on this, you know, they're not too crazy. He's flirting the line of a high risk. You know, he's going up to a 1.5 with just pitch counts. You see a really big spike here after the All-Star break because his chronic load dipped. But this is funny. So June 14th, 1974, he threw 235 pitches, 13 innings. He had 10 walks, 10 strikeouts, or something like that. And his AC ratio was like a 1.3. Just ridiculous. So again, that kind of plays on that concept of a high chronic load being protective of injuries. And I think that we baby a lot of pitchers today, or at least we have them spread out so intermittently that they can't build up enough chronic workload. But I digress a bit there. All right, back to this pitcher who got hurt. We actually we helped him rehab, and this was a really fun experience that led to a product of ours, one of our dashboard products. But we did this by just with some MATLAB plots to begin with. So this is his chronic workload starting December 6th. Remember, he got hurt, took October, November off, started throwing again, and this is opening day, April 6th. We did a simulation in early January. He'd already built up a chronic load to about 4.5. So what we wanted to do is let's linearly ramp him up. You don't need him to be game ready here. We need him game ready opening day when he's going to be making real pitches. So we can take his torque levels per pitch and we can program out throw counts every day. So he wanted to go 5 days on, bullpen on Wednesday, 2 days off. So we used that pattern with that linearly increasing chronic workload, and we just solved for the pitch counts every day that he could do, or the throw counts, not pitch counts. The secondary factor of this was making sure that the AC ratio doesn't spike, because we know above 1.3, well, he got hurt at a 2.1, so we definitely don't want to go there. But we kind of stick to that 1.3 limit, because a lot of research has shown being above that is putting it at risk. And if you kind of integrate this with your mind, you can see it's slowly ramping up chronic load. And on a few days before opening day, he could do 160 throws and AC ratio was, again, like a 1-2. So that's about a 3-inning start if you include the between-inning pitches, the long toss, the bullpen before the game. Pretty good spot for it. So this is where we come into our first machine learning algorithm. This is going to be probably the most supervised version I'll talk about today, and we're not going to get into the back-end stuff. That'll be for the next one. But essentially we have a control theory version where it's like a thermostat. If the chronic load is low, we're always adding workload each day. But the real driving force where we put some negative feedback in the loop is with the AC ratio. So even if we're trying to ramp someone up, if the AC ratio spikes, we take load away. We also only program based on their schedules. If they do any wellness surveys, we can incorporate that. So in our app, they actually rate their arm health every day. So it gives us something to scale things back. And yeah, we have plans to kind of add on to this, which I will talk about. So now users can subscribe to something called motusTHROW, where they track their AC ratio to begin with. So every throw they make gets uploaded for team dashboards. We give them their acute and chronic status. And then if you click on a player, you actually get a 30-day projection of recommended throw counts. You can scroll and get their chronic projections too, but that's the way we communicate to coaches. We give them a daily throw limit, and we show them what their AC ratio will be when they make that throw limit. So this gives coaches a really nice tool to play around with, and it's almost like a load calculator. They get to set their schedules. You can actually go into settings and set up a rotation for a weekend tournament, and we'll give you a little more workload on game days for people based on a rotation you want to optimize. And here's our last ad about the app, but we also give all this information in a mobile app. So we give you AC ratios, your chronic workload level. We talk about that arm health score where you can rate it here. And then we, for kind of like the little leaguers, which is our goal, my dream is to have this on every little leaguer in baseball, preventing injury. That's where all the injuries are happening. So we boil it down into a readiness score. So if your AC ratios are high, you have a lower readiness score. If your chronic load's low, your readiness is lower as well. But the real question, let's see how we are on time here. The real question is, how can we predict performance next? So I talked a lot about injury, but now we're going to go into an example, and this is going to get really deep in the weeds, so I apologize in advance. We're going to go into some matrix math and even some software code to show you how to train a neural net to try to predict performance with AC ratios. So we actually took some data from this year's D2 championship. One of our teams, they are facing, this wasn't an elimination, it was a double elimination bracket, but May 17th was their game day, and it's essentially a must-win situation. And they had 3 pitchers to choose from. They had pitcher A, who was by all means their ace. He actually had pitcher of the year accolades, and but they also had really other good pitchers on their staff. They had pitcher B, who was 7-2, pitcher C, who was 8-2. And the question is, who do you throw? So if we look at their ace, I mean, he's only on 4 days rest. His AC ratio is in a good spot, so maybe. But if you look at his last 2 starts, he pitched back-to-back days, 4 innings and 3 innings. So I think you probably want to be careful with him on this day. We got 2 other guys. You have pitcher B, who recently had a really good performance. If you look back at his guy, he actually had a lot of good traction late in the season. But then here, pitcher C kind of shit the bed a couple weeks earlier. Only on 4 days rest. So I don't know what goes into the decision process here with the coach. I should ask him. But he threw pitcher B, and pitcher B lost. So that sucks, right? So the goal of this is, can we do any better? Can I give you guys another piece of information to try to throw the right guy at the right time? And we're going to do that by trying to predict something called game score from Bill James. Now there's some variety of ways to do this, but the concept is like a quarterback rating for baseball pitchers. So you start with a score of 50, and you get 3 points for every inning you throw, 2 for every inning after 4, 1 point for every strikeout, and then you start subtracting things like 2 points for every hit, 4 for every earned run, 2 for every unearned run, and 1 for every walk. And if you look at the highest game score in MLB history, it was Kerry Wood in 1998, the score of 105, and he threw a filthy 20 strikeout shutout. It's unbelievable. But anyway, so that's the number we're going to try to predict and create models for each pitcher and see if we can have some tool to better pick who should play. And we're going to do it with a neural net. So again, my goal here is to show you how this works. So I think it's important for the layperson, the coach, myself, and other engineers to try to understand what's going on in the back end. So So what we're going to do is give, so this is one, for instance, one game we're going to predict game score for. We're going to take the last 15 AC ratios of the last 2 weeks, and with a 5 neuron model, we're going to end up predicting game score. So that's like the end result of how we're going to do this. What we have to do is train the weights, so the output and the hidden weights. Before we go into that, again, I'm going to show you the calculation first. So after you've solved this neural net, you have these two matrices, and the calculation is multiplying your input by the matrix of hidden weights, and also multiplying it by this output weights. There's also this thing called the sigmoid function, which just makes this even more confusing, right? But all it really is a switch. So for every value in your matrix, if it's a high number, it gets multiplied by 1. If it's a lower number, it gets multiplied by 1/2. So we're giving preference to numbers that are high. Okay, level further, let's look at the matrix setup of this. So your input for the final calculation is a 1/15 vector multiplied by a 15/5 set of weights. So if you, linear algebra, 1/5, if you have these two terms are the same size, your resulting matrix is a 1/5. And these are our A, or our hidden neurons. So that's these A, 1, 2, 3, 4, 5. The next step is multiplying what we just solved for by the 5/1 weights. So the final result is a 1/1 matrix, or our game score. Now, assuming we calculate all these weights properly, that's all it is. It's a really simple matrix math problem you can put in any kind of programming language. So yeah, we're going to solve for 80 numbers. We have a 15/5 and a 5/1. So I'm going to go now and try to show you how we go about doing that. But it starts with just general optimization. So if I had a simple model that just was two variables, x and y, and I modeled the error, our goal would be let's find the combination of x and y to give us the lowest error. That's what we're going to be doing with machine learning, at least training the neural net. So the typical process is you pick point A and B, and you calculate the error. And you can see it gets lower in this direction. So in your software, you step forward in that direction, and you test another 2 points. And you see, all right, what direction is the error minimizing? And using gradient descent, you can keep stepping forward thousands and thousands of times until you find this magical point where the error is minimum. And so we're going to do that too, but instead of just 2 variables, we're doing this for 80 variables. So this is a massive problem that at this point you really can't comprehend these dimensions. So the goal is just, again, showing you, generally we're going to find the combination of 80 weights that give us the lowest error. So the first thing you do is you initialize this 15/5 matrix as just random numbers from 0 to 1. And then we're going to give it some training data. So now we don't have a 1/15, but we have 5 games of data. And you can experiment with this, but the general process I was going through is, all right, as the season progresses, I want to train the model after every start and make it better and learn. So just for this example, we gave it 5 starts. So now we have a bunch of training data, and we're going to multiply by weights and get 5 predicted game scores. For more math love. Whew. All right, so we have a 5/15 multiplied by a 15/5. That gives us a 5/5 matrix of neurons. And you can see if you give it more training data, these matrices get bigger and bigger, but it's all simple matrix math that any programming language can do. And you have your 5/5 multiplied by your other weights that are currently set to random numbers, and you get your 5 game scores. Now we knew how these pictures through because we had their data, so you can subtract their actual scores to get this error. And that's how we're going to start stepping in the right direction. We know the error now. Then there's this process called back propagation, where we're going to update these matrices of weights. So we can multiply our error times the step size, and we say that, all right, the output of this 75, or this is just a 1/5 matrix, it's what it is now, plus error times the hidden matrix we calculated. We also do it for the output matrix, the hidden matrix, but to make things even more complicated, we pass it through this sigmoid function, which is the derivative of the sigmoid function. So in this case, numbers that are close to 0 get multiplied by 1, and numbers that are bigger than 1, or larger, get multiplied by something closer to 0. So back to that kind of gradient descent, we give preference to errors that are smaller, and we give less preference to errors that are big. All right, so that's enough matrix math thing for now. But this can all be done with 16 lines of code. So this is just done in MATLAB. There's 50,000 steps we're going to do, and it's calculating the hidden weights. It's updating the error and back propagating to continue to update the weights. So we do 50,000 times. I'll show you a little animation of how it continues to go. So it moves pretty slow at the beginning, but you'll start to see this 3D plot start to form, and eventually we have, for whatever reason, in the back end, the weights are higher for parts of the training set that mean the most. If you plot the error over every step, 50,000 steps, you can see it starts up pretty high, and eventually we converge on a minimal error. Oof, brutal, right? How well does it perform? This really surprised me. So when we looked at the next 6 starts for these pitchers, this might have been 7, his actual game scores versus what we predicted, and we quantified it as R squared. I mean, it was really, really good. And I think it's almost too good. And I actually think about it, part of that game score is innings pitched, and this coach actually used AC ratio to determine how much to throw someone. So based on their AC ratios, they might have pitched further in a game or less. So it might be confounded by that. But in principle, it's just fascinating how much power this has. I think about it as a pitcher, and I try to think, why did I perform well in a game one day and feel like crap the other? And I think it has a lot to do with what you did to prepare for it. You know, what kind of throw counts were you doing? What was your regimen that week? And this is suggesting that throw counts alone in your activity can predict your behavior quite a bit. So we repeated this process 2 other times for pitcher B and pitcher C. So we had now 6 set of weights. Everyone had their own model based on their own game data, their own performances. And this was the final results that we predicted. So with this knowledge, we could have had game score predictions for the starter, or the ace, the guy who pitched really bad, and then this pitcher C. He actually pitched, like I said, really bad. He threw 7 innings, 7 runs. He had an actual game score of 25.5. And so by all means, I would have picked pitcher C to throw. But everything's already happened, so you can't really go back in time. But it's a cool thought exercise, right? So, yeah, I just kind of did this because I think it's a cool exercise. We don't have this in production, but you could, and you could, in theory, have this going for all kinds of stats. WHIP, ERA. I think relievers could really benefit from this as well. Who in my bullpen is primed to have the most strikeouts today or the fewest hits based on getting up and down the last 3 days? The sky's kind of the limit, and I think that's the point that almost scares me is, there's so much power in machine learning right now that I think it's time to really start taking advantage of it. And that's my goal, So I think the future of sports performance is not just biomechanics based or workload based. It's going to take into account all kinds of variables. So we have some studies going on now with trying to combine sleep and workload data, and that's a lot. But this is going to get bigger and bigger. I mean, we have a lot of technology come out for hydration tracking. I think it'd be great to track nutrition in your macros, even recovery that you do, or mindfulness techniques that you have that help with recovery. I think all these features are going to feed into machine learning models and predict performance and help us decide what to do with our athletes. So that's kind of where I want to end it. I think, again, there's a lot of power here. And yeah, so thanks.
We have time for some questions.
Yeah.
Do you guys take into effect weather data when you're calculating, getting pitchers up and down? Like, you're from here, it's pretty cold in March and April, but now it gets hot. Does that weigh into it at all?
I mean, it certainly could. I mean, there's no reason you couldn't have, weather, opponents. This was just really more for an exercise to show this, but that'd be a brilliant addition. So, yes.
Was the wearable tech producing any data for that score that you were predicting, or just when they were pitching and how much?
So yeah, they wore it for every practice and game. So we had time set every throw they made, every stress they made on those throws, and then they have their statistics are reported on a website. So we just mine that. Yes.
I'm just wondering, so did the coach give rationale for why he threw pitcher B?
We were talking about, I think it might have been a lefty matchup. I'm not sure. But by like, if you kind of look at the stats, I mean, he had the most rest. He kind of had some good traction a few games ago. They played that team a lot too, so they might have had some past stats he was going off of. That's a good question. We should call him. Yeah.
Major League Baseball seems to have this sort of 100-pitch standard, and I mean it's probably one of the most used pieces of data in Major League Baseball. Your opinion of that? I mean, does it just seem ridiculous?
I think it exists for just a reason. I think our conventional wisdom is doing machine learning on its own, so it must be at play. But we actually analyzed Shohei Ohtani's pitch counts, and you guys saw he blew out, or they're doing PRP on him again, but we looked at his workload pattern just from pitch counts only, and they were throwing him once every 7 days, which is what you do in Japan. But we have no idea what he did in the week, so we can kind of assume. But then they had him skip starts. And so I know for a fact his chronic load was really low. And then he had 2 games. He threw 103 pitches in mid-May, and then 100, and that's when he was done. And I think it was probably that 103 pitch game that did it. So for him, 103 pitches is way too much because his chronic load's low. But if you're like Nolan Ryan and your chronic load is built up, you're throwing 150 pitches every game. It's funny, that spike for Nolan Ryan, I'm going to go back to this real quick. So that spike for AC ratio on him, that occurred after a day where he had 28 pitches in a game. So this spike here, that's because he did 28 this day. So he wasn't throwing enough. So it almost did him damage to not keep up a load. But obviously, if you feel like crap, you shouldn't push through fatigue. But yeah, I think just kind of popped into place. Thank you, guys.